Hello, Jon Gabay here. In today's video, we are going to kick off a multi-part series where we design a brain interface. No, we're not going to be cutting open anyone's skulls to insert chips. Instead, we're going to use electrodes placed at different locations to measure and output brain waves of specific bands. Now, the bands we're talking about are alpha, beta, theta, delta, and gamma. These are typically associated with the brain in different states, whether it's concentrating, in deep thought, or in deep relaxation. Our goal is to create a circuit that lets people experiment with creating their own user interfaces from brain waves. This could be for prosthetic control, for gaming, or for achieving deep relaxation states. This is what we hope to be able to achieve. We will be separating out the different waveforms which are present in a narrow band of frequencies, very low frequencies, from less than 4 Hertz up to about 30 Hertz. The block diagram is very straightforward. Shown here is one sensor assembly which contains an electrode, a ground point, and a 60 Hertz notch filter. The 60 Hertz notch filter is very important because 60 Hertz is the most powerful EMI frequency that we are going to be exposed to. So knocking out any 60 Hertz interference improves our signal to noise ratio tremendously. Our signal from the amplifier that is the output of our notch filter goes to our circuit board, which is then separated into multiple filters. The multiple filters are bandpass filters for the individual waveforms we are looking to capture. The output is either as a direct waveform or as an averaged power indicator, which indicates the power in each band. We could use that with an LED bar graph generator or with a regular view meter. The electrode will connect directly to a notch filter that will get rid of any 60 Hertz signal to improve the signal to noise ratio that we present to our main circuit board that has the individual filters. The circuit is based on an op-amp using a twin T passive filter, an RC filter. This is what one stage looks like. Each electrode will have 2 of these in series to increase the performance and to attenuate the 60 Hertz even more. To test our notch filter, we are feeding it 60 Hertz from a sine wave generator to the input of stage 1, which is on the left. Stage 1 feeds stage 2, and we're measuring the output. At 60 Hertz, we are seeing 640 millivolts. Now, as a notch filter, if I adjust the frequency higher or lower, the amplitude should increase. So first I'm going to adjust it higher. We're now at 80, 90 Hertz, 100 Hertz, 130, and we see the amplitude has increased to 2.96 volts, almost 3 volts. Now I'm going to lower the frequency. We'll go to 60 Hertz again. And it attenuates down. Okay, now we're at 60 Hertz. Now as I lower the frequency, we will see the signal level of the output increase. Now remember, we want most signal from around 30 Hertz to less than 4 Hertz. So I'm going to lower the frequency. We're now at 15 Hertz, now at 12 Hertz, 9, 4 Hertz. Look at that, nice signal. 2 Hertz. So we see that we are notching out 60 Hertz and preserving good quality signal level at the lower frequencies and the higher frequencies. Next time we'll tune each individual filter, and then in part 3 we'll integrate the whole system and test it.